mass transfer.
So, Srishti, have you ever wondered how perfume spread across a room even when no one is waving their hand?
Absolutely. That's pretty basic. It's diffusion taking place from high concentration to low concentration.
Yeah, but have you ever considered how fundamental diffusion is to nearly every process in chemical engineering, from gas absorption to catalysis? It governs mass transfer rate at a molecular level.
Absolutely. I think it's very fascinating how diffusion is driven purely by concentration gradients, a concept elegantly captured by Fick's law. The linear relationship between diffusion flux and concentration gradient provides such a fundamental yet powerful tool for predicting mass transport.
True, but real systems rarely allow for ideal, unobstructed diffusion. Take the case of diffusion through a stagnant film, where one component remains relatively motionless while another diffuses through. The additional resistance alters the concentration profile and requires modifications to basic diffusion equations.
Yes, and that's where the shell balance method becomes essential. By applying differential momentum equations to thin control volumes, we can derive velocity and concentration profiles, giving a more precise understanding of transport phenomena.
It's remarkable how these principles extend to multi component systems as well. Unlike simple binary diffusion, where we can rely on Fick's law, three component diffusion requires a more complex approach. The interaction forces between species necessitate the use of Stephen Maxwell equations, which account for molecular friction and interspecies coupling.
That's a great point. Multi-component diffusion is particularly important in industrial applications like gas separation, combustion, and membrane technology, where the simultaneous movement of multiple species affects efficiency and performance.
Exactly. Understanding these transport mechanisms is crucial for optimizing reactor designs, improving mass transfer rates, and even predicting environmental pollutant dispersion. Diffusion, in essence, is not just a molecular phenomena, it is governing principle of large-scale industrial processes.
Agreed. It's amazing how something as fundamental as molecular motion translates into complex engineering challenges. We often take it for granted, but without these models, designing effective chemical processes would be nearly impossible.
Well said. It's a testament to how foundational transport phenomena is in engineering. Now let's delve into the governing equations.
So, Srishti, you talked about shell balance for mass transfer, but I was wondering how it all started. Who even came up with this idea?
Oh, that's a cool story. It all goes back to the 19th century. The foundation was led by Adolf Fick in 1855. So now let's talk about Fick's law. As we heard previously in the video, that in 1850s Adolf Fick conducted two diffusion experiments and gave us the two Fick's law which he is most known for. The first law, which is Fick's first law, relates molecular flux to concentration. Now what is molecular flux? Molecular flux is how much of a molecule is passing through an area over some time. So if we consider a square rectangular box and this a square plane in that rectangular box, some molecules are placed here, some molecules are placed here. So in a unit time, the number of molecules that will pass through this plane in this planar area, through this planar area, is molecular flux. So its unit will become molecule quantity that is passing per area into time. This is molecular flux. For molecular flux to take place, uneven placement of molecules should be there. For example, if one molecule is passing from left to right and two molecules are passing from right to left, so the net flux would be one molecule passing from right to left. So there has to be an uneven placement of molecules for molecular flux to take place. So this, if we consider concentration versus coordinate graph, it becomes a straight line, and the parameter that relates these two quantities, as we know it, is the diffusion coefficient, which is denoted by D. So the flux, which is denoted by J, is given as minus D by dC by dx. This is the Fick's first law, where D is diffusion coefficient, C is concentration, and x is the coordinate or position. This is for 1D. If we consider it for 3D, then we will consider y and z coordinate as well. So it will become as minus d bracket dc by dx, movement of molecule in x plane plus movement of molecule in y plus movement of molecule in z. This is Fick's law over 3D. Now, what is Fick's second law? So Fick's second law relates concentration change over time with changes in space. So for example, here we studied concentration and x coordinate. Here it is linearly varying. So the first derivative is positive, but the second derivative is 0, because it is increasing at a constant rate. But if we consider a slightly curvy graph like this, here also the concentration is increasing with space, but so the first derivative is positive and also the second derivative is positive, because here it is accelerating the concentration, which is changing over time, but how fast it is changing, that is what the second derivative gives us. Here the second derivative is positive because the concentration is increasing with time. So the second law relates the concentration change with the stiffness of the graph. So how fast the concentration is changing, that is what the second law gives. This is again for 1D. If we apply it for 3D, it becomes dc by dt. Here d is again diffusion coefficient into d square by d square c upon dx square plus d square c upon dy square plus d square c upon dz square. This is for 3D. This is the Fick's second law.
Right.
Now we will move on to the
We
second.
propose the Fick's law of diffusion, which describes how molecules move from high to low concentration.
Wait, so you are telling me that Fick was the first scientist?
Well, not exactly. Fick did give us the basic equation, but the shell balance method, as we know, came later. Engineers needed a way to apply Fick's law to real world problems like evaporation or chemical reactions.
So when did people actually really started using shell balances?
I think it would be around 1900s, thanks to Ludwig Prandtl, the same guy who worked on fluid dynamics. He introduced the boundary layer theory, which used differential balances for momentum transfer. Engineers then realized that hey, we can do the same for mass transfer as well.
Can you explain what boundary layer theory is? Some of us might not be aware of it.
So boundary layer theory basically describes how a fluid flow near a solid surface. For example, how wind will flow when it is moving across an air wind. So you might ask, why was it revolutionary? It was revolutionary because before Prandtl, engineers treated entire fluid either as ideal, which made the equations too simplistic, and either viscous. So for viscous, Navier-Stokes equations are used, but it made the problem very complex to solve. So after it was discovered, it allowed for simplified equations and for real world problems.
That makes sense, but how did it evolve?
In the 1920s,
Lewis and Whitman developed two-film theory for gas adsorption. They used a simplified shell balance to model diffusion across thin films. It was a big deal for designing scrubbers and distillation columns. So, what was two film theory?
So, the two film theory proposed by Lewis and Whitman in 1924 explains how a gas molecule, say for example CO2, dissolves into a liquid like water through absorption. It assumes that there are two films, one gas film and liquid films, which exist at the gas liquid interface. So, mass transfer happen by diffusion through these stagnant films. The key idea of it is that the slowest step, which is the rate limiting step, controls the absorption. Like, it is almost like crossing two security checkpoints. Whichever is slower will decide your total waiting time, right? How does it work? So, the step by step process involves a gas molecule, like we said CO2, moves from the bulk gas phase to the gas liquid interface and diffuse to the gas film. Here in the gas film, it encounters a resistance, which is 1 by kg. The kg is the gas mass transfer coefficient. At the interface, the gas and liquid concentrations are assumed to be in equilibrium, which is given by Henry's law. Similarly, now the gas molecule, after being at the interface, it diffuses through the liquid film, and here it encounters the resistance, which is given by 1 by KL. Now KL is the liquid film mass transfer coefficients. Finally, then it dissolves into the bulk liquid. So that is how a molecule moves from bulk gas to bulk liquid. And this is known as two. In physical chemistry, Henry's law is a gas law that states that the amount of dissolved gas in a liquid is directly proportional at equilibrium to its partial pressure above the liquid. So that's why a soft drink gets less fizzy quickly. So the equation goes like PA is directly proportional to XA. Now PA is partial pressure of gas above liquid and XA is the concentration of moles of liquid. To remove this constant of proportionality, a constant is used, which is the Henry's constant. So KH is the Henry's law constant. So we know that the greater the pressure above the liquid is, the more gas it will dissolve. So the schematic diagram for the two film theory goes like this. Consider this is the phase interface of gas and liquid. This is the gas phase. Now this is the gas film. Here is our liquid film and here is bulk liquid or liquid phase. Okay. So let's denote the thickness of the gas film by some variable delta G, and likewise for the liquid film thickness by delta L. So gas molecule, which is at partial pressure PA, moves from the bulk gas into the gas film and then at the interface. We know by Henry's law that at interface it is at equilibrium. So let it be denoted by PAI. Now at the interface it moves now into the liquid film. Here it is denoted by concentration CAI. Now it moves into the liquid film and then moves into the bulk liquid and we get a concentration CA. So this is the mass transfer direction from gas phase to liquid phase.
Okay, but who made shell balances mainstream?
I'm sure you all must have heard about him. The legends Bird, Stewart, and Lightfoot. In in 1960, they published Transport Phenomena, the Bible of chemical engineering. They formalized shell balances for mass, momentum, and energy transfer. Suddenly, every engineer had a systematic way to derive governing equations.
Wow, so they are like the Einsteins of chemical engineering.
Exactly. But before them, engineers relied on empirical correlations, basically educated guesses. But Bird's team gave us rigorous math to predict concentration profiles, reaction rates, and more.
So, are there any real world examples?
Yes, in 1950s, researchers studied CCl4, which is also known as carbon tetrachloride, evaporating O2 in a tube. They measured the evaporation rate and used shell balance to calculate diffusivity. It was one of the first experimental validations.
Wow, that's so cool. So, shell balance wasn't just a theory, it actually worked.
Yep, and today we use it everywhere from designing fuel cells to modeling drug delivery in the body.
Is it still used today?
Absolutely, but there are limitations like assuming constant diffusivity or ignoring turbulence. For complex systems like nanoparticle diffusion, we now use computational fluid dynamics.
Oh, that is CFD, right?
Yes. So now, Srishti, to summarize it, can you please give the key takeaways?
Absolutely. So, in 1855, Fick gave us the diffusion equation. In 1904, Prandtl introduced the boundary layer theory, inspiring mass transfer models. In 1920s, Lewis and Whitman developed the two-film theory using shell balance concepts. In 1960, Bird, Stewart, and Lightfoot formalized the shell balances in transport phenomena. And now we are on the modern use, where it is still foundational but supplemented with CFD for complex systems.
It's crazy that what we studied in a semester has been evolved during many, many years.
Yes.
Prashita, I'm stuck on this shell balance concept. It is so difficult. Can't some alternate method be used instead of this? I mean, what is its significance? I don't get it.
No, you absolutely cannot use anything else. Why? Let me explain you. Shell balance is one of the most fundamental methods for analyzing mass transfer. Without it, we wouldn't have a structured way to derive equations for diffusion and convection.
But why can't we just use Fick's law of diffusion?
Fick's law tells us the diffusion flux, but it does not account for varying concentration profiles in different systems. Shell balance helps us systematically derive the governing equations for different geometries and boundary conditions. Think about industrial applications like absorption, distillation, and even drug delivery. Engineers use shell balance to predict how mass transfer happens inside reactor, pipe, and membrane.
That makes sense. So it is widely used in chemical, environmental, and biomedical engineering. For example, when we are designing catalytic converters in cars, engineers use shell balance to model how pollutants diffuse and react. Thank you, Prashita. I think I finally get why I have to study shell balance.
Glad I could help. Now let's apply it to a problem and see how it
So our
works.
video would be divided into four parts, and it would be structured as follows. And the first part would be where we have already talked about the introduction, history, limitations, and significance. In the second part of the video, we will see that what is shell balance equation and how it is written, and then we will take the following cases. The first cases that I would take is shell balance for mass transfer in a stagnant film where A is diffusing through non-diffusing B, and the second case would be
Then we will look diffusion through three component system, where one is your water species and the second is your binary system. So that way it is diffusion through three components. Then we will also look at quasi steady state problems and solve two problems in this. And then we will go through some discussions over the topic.
finally we will see what all we have studied in the entire video, and we will end with some concluding statements and discussion.
Now we will move on to the second part of the video where we will learn about shell balance or mass transfer. where we will see the theory, equations and some problems.